Yesterday you were talking about three different functions: linear, exponential, and quadratic. We talked about these a bit in chapter 4 as well. We were identifying them from their graphs yesterday. Today we're going to work on the tables with them. So it says when the x values in a set of data pairs have a common difference, you can analyze the data numerically to find the best model, the model being linear, exponential, or quadratic. You can use a linear function to model data with y values that have a common difference. So right here, you notice the difference between each set of numbers is 3. The difference of 5 and 2 is 3. The difference of 8 and 5 is 3. If you notice that it has a common ratio, a common multiplier, I'm going to write that underneath here, then it's an exponential pattern. And you'll notice that 1 times 2 is 2, or 1/2 times 2 is 1. You'll notice that same pattern going on as these keep increasing by 1. Now, if it is quadratic, it doesn't have a common difference. It has a common second difference. These are a little bit trickier to spot, but one thing that will make them stand out is that as you kind of look along your list here, these numbers don't seem to match. If you were to take -1 minus 1 and get -2, 1 minus -1 is 2, 7 minus 1 is 6. These numbers don't match, but you're also not multiplying. You couldn't say 1 times 7 is 7, 7 times 7 is 17. So you look then, once you copy down that first difference, then you check the difference between each of these. The difference between -2 and 2 is 4. The difference between 6 and 2 is 4. And the difference between 10 and 6 is 4. These are the graphs that create those parabolas like that. They get steeper and steeper as they go, so the jumps between numbers have to be greater. So if you look right here, you see that it has a common difference of -4 every time. So it's dropping by 4. That represents your slope, that change in y over the change in x. Then you need your y-intercept. So your slope is -4. You'd write an equation starting like this. -4 goes in for the slope. -3 is your y-intercept. And you can write your equation or your rule to model it. Here you have what's called a second difference. If you look, you can tell it's probably not multiplying to get from one to the next, but the difference between each number isn't consistent. So you check the difference between those and they're all the same, -0.5. These equations we will write as only ax squared plus c. We're not going to do ones that have bx in there. You're just going to need to find that leading coefficient and your y-intercept. To find this, though, right here, you take your second difference and divide it by 2. So to find the value of a equals the second difference divided by 2. So if I took 0.5 or -0.5, divided it by 2, that would be -0.25 x squared. And the y-intercept would be +0. That is noted, this second difference divided by 2 is also noted right here with another example if you want to see that too. But like I said, we're not going to do ones that have that middle term of bx in there. So you're going to see tables that you need to write a rule for. You look right here, you notice that this one keeps multiplying by 2. If it's multiplying, you're going to use this model, a times b to the power of x. I know that because any exponential pattern, multiplying ones, common multiplier, you need to use this rule. This rule is going to need a common multiplier number, and then the number was 0. So it keeps multiplying by 2 every time. The number 0 is a 1. So you could technically leave that 1 off or put it in. It's multiplying, so the 1 doesn't have to be there. I just always write it. Let's take a look at our next one here. This one says, which type of model best represents this pattern? Now you'll notice in this one right here that the change isn't consistent. Here it's dropping by like 24, but then here it only drops by 5. So we know it's not linear. We could go about checking to see if it has a common second difference. So do 24 and then your 4.8 and then keep checking to see where it's at. We can also look and see, this looks like it's dividing by 5. And then say, well, if I took 6 divided by 5, would that be 1.2? So you can check your 6 divided by 5. You can take that and divide it by 5. And you keep getting the next number in line, right? Now, that tells me that I actually have a common multiplier, but that common multiplier isn't 5. It's 1/5. If I noticed a pattern of dividing by 2, I'd use the number 1/2. Dividing by 3, I'd use 1/3. I'm going to take my y-intercept, my value for a, my common multiplier. Remember, when it's dividing, use a fraction to the power of x. Now this one is a little bit different. This one hops around a little bit on you. So I want you to just pause the video quick and identify the space. So subtract, find the space between each one of those. Some of the problems you're going to see in your homework, and I think if I remember right, there's really just one where this happens. The pattern is more like a natural set of data where the numbers aren't perfectly increasing or decreasing by this exact amount every time. They're sort of off just a little bit. It's definitely not multiplying though. And if you went to find a second difference between all of these, they wouldn't be consistent either. It seems like it's increasing by about 480 every time. So here I would say, well, if this is an increase of about 480, that makes it linear. So I would have y equals 480 times x plus 18,254. Y-intercept there. This, you can be super specific and average them, or you can just be like, well, 480 is about right. You can do what works for you. I usually just kind of give it a good guess, you know. All right, turn the page. We're going to practice just a couple here. It says, which type of function best models it, and write the equation. So again, linear, mx plus b, exponential, a times b to the power of x. Quadratic is a x squared plus c. No b in those ones. So I'm going to look at this one first. I notice that if I subtract, if I take 11.2 and subtract 2.8 from it, 11.2 minus 2.8, I get 8.4. 2.8 minus 0 is 2.8. If I subtract 25.2 minus 11.2, I get 14. And when I subtract these two, I get 19.6. I look and I see these are all different. I can check multiplying really quick, but quick tip for multiplying is that if the pattern is exponential, it can't have a 0 in it, because the only thing that would give you a 0 as an answer would be another 0. So it's not multiplying if it has that 0 sitting there. Now I'm going to check that second difference. So I'm going to say 8.4 minus 2.8. That's 5.6. 14 minus 8.4, also 5.6. Also 5.6 here. So this is that common second difference. I'm going to take 5.6 and divide it by 2. The value of a is the second difference cut in half. So that'll be 2.8 x squared. I'm just going to write over here a 5.6 divided by 2. And then grab up that y-intercept here of plus 0. And obviously you don't need to write the 0. I sometimes do just while I'm working. You'll notice on this problem where, and this is usually a tip-off that you have exponential. First of all, you don't have 0 with 0. but it is decreasing here or increasing. But notice how the decimal has to keep going out further and further and further. That's usually an indicator that you are dividing. So if I look here, it looks like I'm dividing, but remember, you need to go backwards. You can take 2 divided by 5 like that to find the number it's multiplying by. So if you can't figure out what it's multiplying by, go backwards and divide. So it's 0.4, 0.4, and they're all 0.4s. You get your start number or your initial value. Pardon me. What you keep multiplying by, excuse me, and then you put it to the power of x. And if you're ever thinking, gosh, I wonder if I did this right, I feel like I didn't, just take and plug in something like 4 right there and see if you get 0.128 back. So if I say 5 times 0.4 to the power of 4, check my answer, I get the answer back if I plug that in. You know you're doing it right. On this one, you'll notice that it is also decreasing, but you can see those consistent drops every time. So it's dropping by 0.5. It's dropping by 0.5 every time. And then you grab your y-intercept here. So it would be y equals negative 0.5 or negative 0.5x plus 2. So this one is linear. I wrote an mx plus b equation. This one was exponential. I wrote an a times b to the power of x, where it starts, what it multiplies by. And by start, I mean the value is 0. This was quadratic, ax squared plus c. Sometimes you have to kind of mess around a little bit with the numbers until you can figure out the pattern. Some of them just jump right off the page at you too. It kind of depends.